Okay, so what I'm going to do now is describe how to find a subobject classifier. Okay, so what I'm going to do now is describe how to find a subobject classifier in one of these categories of functors from C to set. Now, the objects in this kind of category are functors from this category C, which could be any category, to the category set. And the arrows in this category are natural transformations. Now, you can basically work component-wise in this category to think about things like products and pullbacks and all the rest of it, because if you just pick a particular object in C, then the functors in this category are going to send that object to different sets, and the natural transformations are going to have, and the natural transformations between functors in this kind of category are going to have components associated with those sets. And so basically you can sort of work component wise. Now, I'm not going to go into how to do general stuff in this video about how to find pullbacks and all the rest of it. But I think you can probably work that kind of stuff out for yourself. It really is sort of quite simple if you just sort of work component wise. Just for example, if you want to work out a pullback, let's say you have natural transformation from a functor f to a functor h called tau, let's say, and another transformation sigma from a functor g to a functor h. Well, if you just look at if you just pick an object A of the category C, then there's going to be the kind of eighth component of tau going from f of A to h of A, and the eighth component of sigma going from g of A to h of A. And so you have these two kind of functions going into h of A, which is a set, and then you can just work out the kind of pullback of that just as you would working out an ordinary kind of pullback in the category of sets. Okay. Anyway, I'm going to describe how to find a subobject classifier, because that's more difficult, and you get these very, very interesting kinds of ideas of logic from this, because each of these functor categories, these structured set categories here, is a topos. Now, I'm going to be very kind of now I'm really going to just rush straight through this. I'm not going to explain anything. I'm just going to give you the recipe for making the subobject classifier of a functor category like this. If you're interested in the details, I highly recommend Robert Goldblatt's book Topoi, The Categorical Analysis of Logic. But anyway, let's go. So for an object A of the category C, let SA denote the set of arrows which have A as their source, the set of arrows of C which have A as their source. Okay. Now let's define an A sieve as a subset X of S of A, which is so-called closed under left composition. So that means if we take a element F from X, in other words, if we take one of these arrows from this subset X of S of A, and we take an arrow G of our category C, which can be composed after F, then we have to have that G after F is also in X. Okay, so this subset X of arrows out of A has the property that if we compose them with other if we compose other arrows after them, we just get other arrows in X. So that's what we mean by an A-sieve. Okay, now we define the functor from C to set, which we call omega. This is basically our subobject classifier, such that for an object A of our category C, we have that omega of A is the set of A-sieves. So that's how this functor works on object A of C. How about arrows? Well, let's say we have an arrow F of our category C, which goes from an object A to an object B. Now, omega of F is obviously going to be a function sending omega of A to omega of B, and that's going to send an A-sieve X to the set of arrows from B to some object D, the set of arrows G, which are such that G after F is a member of X. Now, this functor category set to the power of C, this category of functors from C to set, will have a terminal object, and we might as well suppose it has this form, since it, there will be a terminal object of the form I'm about to describe, and that is we can suppose that the terminal object 1 of set to C is the constant functor. Which just sends all the objects of C to this singleton set containing 0, and it sends all the arrows of C to the identity arrow of 0. Now, what about the truth arrow? Well, that's going to be an arrow in this functor category, so it's going to be a natural transformation from the terminal object to this functor omega, and so it's going to have different components because it's a natural transformation. So we suppose that the 8th component just sends 0 to S of A, the largest A-sieve. So remember that omega of A is just the set of all A-sieves, and this includes S of A, also includes the empty set, which is another kind of degenerate A-sieve. Okay, so suppose that we have a monic, I should say a monomorphism. I used the wrong name for it, monomorphism. Suppose we have a monomorphism in this functor category, so that's a natural transformation from a functor F to a functor G in this category of functors from C to set. Well, I want to tell you how to find the classifying arrow of such a monomorphism tau. Now, for simplicity, I'm just going to, so since this is a monomorphism, that means that the 8th component of this natural transformation for any object A of C is itself going to be a monomorphism. Okay, so it's basically kind of a load of components which are just injections of sets. Okay, now for simplicity, I'm going to suppose that every component is actually just an inclusion function. Okay, so for every object A of C, we have that tau of A is just a inclusion function that just includes this set f of A into G of A. Okay, and now this characterizing arrow here, phi of tau, well, that's going to be a natural transformation. Oh, I went wrong here. I should have said for every A in C, we have the, whoops, no, that's okay. So now phi of tau is going to be a natural transformation from G to omega, and this is our this is our classifying arrow, and so this is natural transformation. Now the eighth component of this is going to be a function from G of A to omega of A, and that's defined so that for every member X of G of A, we have the phi of tau of A operating on X just returns the set of arrows F from A to some object B, which is such that G of F operating on X is a member of F of B. And that's it. That's how you can find the subobject classifier, the truth arrow, and the classifying arrows in this topos, which is this category of functors from a category C to set, at least when the monics that you find in classifying arrows of have inclusion functions for each component.